Let's do lab 21, part 1.1. So this is just showing the basic operation of a CMOS NAND gate. And the most mysterious part of this part of the lab is why do we have the pull-down resistors? So actually you could ask, why do we have all three resistors? One question is, why do we have this resistor? And a CMOS logic output is a very good voltage source. So if you connect a very good 5-volt voltage source directly across an LED, then you will burn out the LED. So we have the 100 ohm resistor to limit the current through the LED. So that one is easy to explain. These two are a little harder to explain. So if the switch is closed, if I push the button, the switch is closed. Then I have a 0 ohm connection to plus 5 volts, and that is fighting with a 100 ohm connection to ground. So 0 ohms easily beats 100 ohms, so you get plus 5 volts. If you leave the switch open, then you have a 100 ohm connection to ground, and you have an infinity ohm connection to plus 5 volts. 100 ohms easily beats infinity, so you get 0 volts. So that's the idea. See, if this were a connection with no resistor, you'd get ground when the switch is open. When you close the switch, you would have a direct conflict. You'd have two very low impedance paths, one to ground, 1 to 5 volts. You basically be short-circuiting your power supply to ground. So that wouldn't work. And if you didn't have this connection at all, then when you close the switch, you would connect to 5 volts, but when you open the switch, you would have no connection to anything. You'd have a floating input. So you need to be actively connecting either to plus 5 or to ground. And so the way you can do that with a simple switch like this is when the switch is open, you go through the resistor to ground. When the switch is closed, you go with a low impedance, basically 0 ohms, to plus 5, and so the 100 ohm path doesn't matter in that case. Okay, so I wired this up here. So we have, first of all, always connect pin 14 to plus 5 volts, pin 7 to 0 volts, pin 14 to plus 5, pin 7 to ground. Black wires here are ground. The red wire here is plus 5 from the Analog Discovery 2 board. Then the yellow wire is going to pin 1. Blue wire is going to pin 2. So pin 1 and pin 2 are the two inputs of this first NAND gate in the device, and pin 3 is its output. Pin 3 is going through a 100 ohm resistor to the positive end of this LED, and then the other end of the LED goes to ground. Meanwhile, what's happening on the left with the push button? It's a little harder to see, but I made them sort of span across here. I couldn't remember which way connects to which when you push the button. So this way, well, I know the diagonals get connected, so I don't even have to figure it out. So, although I think what actually happens is this gets connected to this. And anyway, okay, so I have 5 volts going to this top left corner, 5 volts going to this top left corner. This bottom right corner is going to my logic gate input, and it's also going, this bottom right corner is also going through a 100 ohm resistor down to ground. So now this matches the schematic diagram. And when I don't push any buttons, the NAND output is true. When I push just the left button, it's still true. I push just the right button, it's still true. If I push both buttons at once, see, it becomes false. And I guess you have to take my word for it for what my two fingers are doing. But if you look up at my scope display, Here's no buttons. Here's left button only. Here's right button only. And here's both buttons together. And to make that nice display, I did 2 volts per division. I offset one channel by 1/10 of a volt so you can see the red, the yellow and the blue traces together. I did 1 second per division, and I put it in shift mode. So shift mode seems to be what this oscilloscope calls roll mode. So when our scopes in the lab, they call it untriggered roll, and I made the trigger be none. So no trigger and shift mode, which seems like roll mode. And then you can, it's kind of nice, you get like a chart recorder display of the recent history. Unfortunately, there are only 2 channels, so I can't show you the output at the same time, but here, let me zoom out. Maybe you can see that. So, you can't quite see that. Let's see. So, no, I don't see the light. Maybe the light is there. I don't think, well, I can't tell if you can see the LED. So, okay. Good. So that's pretty decent. Okay.